Okay, thumbs up. Good evening, everyone. If I may have everyone's attention, it's just a little bit after 7:15. Actually, it's almost 7:17 already. If I could have everyone's attention, I'd like to welcome everyone. Large audience here, such a large crowd. Thanks for coming. Before we get started with tonight's guest presentation, I have a few announcements to make. First of all, I'd like to thank all the members who showed up for the meeting last month. I'm just going to turn down, bear with me a minute, I'm going to turn down the faders in the back. No, I got it. I'll be back because I remembered what I turned off.
Lawrence has left the building.
Oh, well, thank you very much. Thank you. Yeah. All right, so here I am again. Starting back where I left off, I'd like to thank all of the members who showed up at our annual business meeting last month, where we elected the board of directors for this next year. I'm returning as president this year, and we have all the regular cast and crew with Kevin Sintulis as vice president, secretary Dan Hislop, treasurer Jürgen Petal, observatory director Dave Lakepart, our at-large member, one of our at-large members is Martin Mika, and the other one joining us this year is Chris Eltner, who, for those of the newbies who were at our new members meeting a little while ago, you all know Chris.
Yeah,
So
I ran
right
the beginners meeting by sitting there with my mouth shut.
So I'd like to thank everyone who voted, and I would like to thank the board of directors for volunteering their time for this next year. And with summer upon us, I'd like to go over some events that are coming up. This Saturday, June the 21st at 8 p.m., we are going to have our next scheduled star party. Now, for those of us who are newer to the club, we don't just have star parties. If you join our MAS Observers Gmail list, when anytime, any day of the week, people might decide, hey, tonight's going to be a really good time for observing. Let's just all go out to, I'm going to go out to YRS. Who's going to join me? So star parties happen that way. But then we also try to have once a month on the Saturday closest to the new moon, have a scheduled star party just to have something for everyone to look forward to. So on Saturday, June 21st will be the next one. Hopefully the weather is good this month. And if it is or isn't, we'll still make a weather call by 4 p.m. that day, and cross your fingers. So it'd be great to see a bunch of people, especially newer members, joining us for the star party. Also on Friday, July 11th is going to be our next monthly meeting right here at UW Space Place, 7 p.m. And next month's guest presentation is going to be entitled The Role of Oceans in Earth and Exoplanet Climates. John, did you want to give us a little primer on that presentation?
So the only thing I'll say about next month's meeting is that Hannah Zanowski, who is a professor in oceanic and atmospheric sciences at UW-Madison, on her website, Hannah says, and I quote, "My first love is astronomy." And when I read that about Hannah, I knew we had to get her here, and she works on exoplanets and especially exo-oceans. It's going to be a great talk. Don't miss it.
Sounds fascinating. It's a topic that we don't get to hear about too often, so it sounds like it's going to be a great meeting to be at. All right, going to the reverse side of my piece of paper here, my notes. So further off, I just wanted people to kind of circle some dates on their calendars. We have a public outreach meeting, a public outreach star party at Donald Park on Saturday, August 16th. And with all these, more details will be announced as we get closer to those. But that's always one ones, because usually we try to get that star party so that it's as near to the peak of the Perseid meteor shower as we can possibly get. So that's Saturday, August 16th, Donald Park, that's nearby Mount Vernon and Mount Horeb here in Dane County. Saturday, September 20th, we're reserving that for the annual MAS picnic at YRS. And since that Saturday night's close to the new moon, hopefully we can do some observing that night. Tentatively, we'd like to have a rain date if the weather isn't so good for the picnic on Saturday. We'll try to do it again on Sunday, September 21st. And then Friday, October 3rd, there's gonna be Moon over Monona Terrace. The show is gonna go a little longer this year from like, I'm trying to remember exactly if it's 7 to 10, I believe.
Yes.
7 p.m. till 10 p.m. So setup's gonna be a little earlier. For those of us who might wanna be involved in the pre-planning, we are, early in September, we are going to have a Zoom meeting to plan Moon over Monona Terrace. So let me know if you're interested in providing your 2 cents for that. Also, for those of us who like doing the electronic observing EAA, electronically assisted astronomy, we're gonna try to do, right before the event, we're gonna try to do a run through so we encounter it for those of us who need to cast from our portable pads or smartphones to a TV monitor provided by Monona Terrace, that there's as few technical hiccups as possible. All right, so yeah, mark those dates on your calendar. Now, I do believe Dave wanted to make, there was some sort of Yana Research Station associated announcement that, or Kevin, you can?
I can do. Dave is probably going to put out something to Madison observers on email on this. In the past, those of you that have been to YRS realize we have a logbook right inside the door. It's kind of a historic logbook, goes back to the 1970s, I think.
85.
Was that?
85.
85, okay. Then when we first got down there at Yana, and it really records a lot of great stuff in there about people coming and going, what they did, and on different dates. We always encourage people to use that, especially when you go into the clubhouse and you're accessing stuff in the clubhouse. We've been kind of lax on asking people to enforce that, and I'd like to really start that up again. If you're intimidated about signing that book or something like that, you shouldn't be. If you look at the entries in it, there's, I think lately the entries have mainly been Dave and myself, but and not too many other people have been using it. But we'd really like to do it, especially with, thanks a lot, Rick. With people checking out equipment, we've had a resurgence in people checking out equipment, whether it be a Dob or whether it be the Sea-Star. And to save some confusion over where that equipment might be, it would be nice that people just could go over the logbook if they see it missing, and then go over the logbook and see, okay, I know who has it. God forbid we should ever try to call the police and think it was stolen and someone has it at home. So I'd like to be able to encourage people, please, especially if you're checking out equipment, please note that in the logbook.
Don't call the police, I have that Meade eyepiece, just found it in the house.
And in a similar note too, for anyone who's using YRS and you notice that there's an issue or something, you can use a logbook to write down, oh, I saw this outlet over here this electrical outlet over here is not working. Or you notice something else interesting with the facilities at YRS, you can just put in a note in the logbook. Or if you're there and you happen to work on a little project and maybe reorganize something, straighten some things out, or do some sort of little project at YRS like watering trees, you can write in the logbook, I watered trees the new trees on this day. So all that information really helps. Or if you had a really good time, you can jot down in the logbook something that you really enjoyed observing that night too. People enjoy reading those things. So I encourage everyone to use that logbook. Oh yes, Frank?
Would I ever write in that I helped you set up your telescope and it took more than a half hour? Because it's such a fantastic telescope.
Yes.
All right, so that's very good. So, all right, I'm trying to think of any other announcements and I'm drawing a blank. Jürgen, yes. The electronics for this microphone are my bag.
Okay, no, it's okay. I just want, twice tonight, MAS Observers List has been referenced. When we changed our membership categories last year, we used to have regular observers who were not put on the observers list. And a lot of people did join, most people who had been regular observers did move over to the new category of general. But I did not, in a systematic way, move those people onto the observers list. So if you wondered what observers list is and you haven't been getting any, let me know and I'll put you on the list.
Yeah, and just to.
Oh, and I'm sorry, one other thing. For those who are curious, we have 145 members. We just had a new one back there, John. So.
And just to add on to what Jürgen was saying, because not everyone, we have two lists. We have the members list that's basically a mechanism for the board of directors to communicate with everybody in the club. Everyone who is a member needs to be on that list so they can get the monthly announcements and get the newsletters and things like that. The MAS Observers List is a more optional list because not everybody, sometimes people request to be taken off that list because they're like, I don't want to get that many emails, or if you're getting more emails than you want, you can always select the daily digest option on there. But for people who want to use Yana Research Station, or if they want an outlet to talk about astronomy subjects and you don't know how to contact other people in the club, the observers list is a great forum to contact people about fun astronomy subjects if you're not, say, on our Facebook group. So.
And if you want to ask to be added to it, just send one to the club's open email address and you'll channel it.
Okay, yeah. Could you say yeah? It's to the channel, to the club. So because to get on it, you have to contact Jürgen, who is our treasurer. And if you email me, the Dyremore at charter.net, that's on the club emails, or if you go to the website and do you use the email address that's on our website, you can get in touch with that optional email list that way too. We'll get you set up one way or the other. Any questions on it? Yes, Rick?
Not on that.
Oh,
I had a 15-second announcement. Nebraska absolutely rocked. It was a terrific trip. Am I right or am I right? Yeah. Mr. Rummel, thank you ever so for organizing that. If you didn't know, about 5 or 6 of us went down to the Merritt Reservoir State Natural Area and camped there for several nights, and we had some amazing skies, and we had amazing adventures too.
if you hate light pollution, you'll love this Reservoir State Park in Nebraska.
If you hate sand, don't go.
Anakin Skywalker will not be there. All right. I just wanted to, I guess if we have a new member, would you both like to introduce yourselves to the group, or are you being kind of low-key? You don't have to if you don't want to.
Everybody stare at the nude.
Who's wearing a very chic NASA pullover sweater, by the way. That's really cool.
Well, hi, I'm Lane. Recently moved to Madison and like astronomy.
It's a pleasure to meet you. It's a pleasure to meet you. And what's your name? My name's Lawrence.
I'm Julia. I'm just tagging along with him because I have to listen to him talk about space all the time.
Both in the right place, and it's great to have you here. We hope to see you around.
You will be assimilated.
And I do see.
Hello.
Great. I should have got these. That's what I get for looking at my watch. It is that time to introduce tonight's guest speaker. John, would you care to do the honors?
So I know I always seem excited about our speakers, but I'm really excited tonight. Juliette Becker is a professor in the Department of Astronomy. People who I've talked to before know that I complain sometimes about our astronomy department here at UW-Madison because everybody is a cosmologist or extragalactic, dust in the universe. There are very few people in the department who are interested in anything that happens inside our solar system. And Juliette and I were talking earlier, she may be the only person. And exoplanets is one of her areas. Many of you know the story of Mike Brown, the astronomer at Caltech, who his research kind of led almost directly to Pluto being demoted in 2006. A couple of years later, Konstantin Batygin, they've done a lot of work on the theoretical exoplanet, or the theoretical planet, Planet 9, hypothesized to be in orbit around our sun. Juliette was part of the team at Caltech who worked on Planet 9, and that's a part of what she's going to talk about tonight. So please give a warm welcome, Juliette Becker.
I'm sorry to interrupt. Yeah, before we get started, and Julia, do you have any preferences or questions? Because we have some really inquisitive people here. Do you?
Yeah, just go ahead and interrupt with questions.
All right, that's good. And just a reminder, for the courtesy of the people in the audience and the courtesy of our speaker, if you have electronic devices, please put them on silent during the presentation. Thank you. And Julia, go ahead.
All right, thank you so much. All right, is that me or you who's making the? Okay.
Could be out.
All right. Okay, great. Well, John, thank you so much for that wonderful introduction. So I'm super happy to be here to talk to you guys today. So what I'm going to be talking about is kind of two things today. First, discovering planets in the solar system. And discovering planets in the solar system has a much longer history than the amount of time that I've personally been in the field. But I'm also going to talk to you about the search for Planet 9 specifically. So what is Planet 9? Why do astronomers, led by Mike Brown and Konstantin Batygin, think that it exists? What's our evidence that it does exist? But also, why haven't we actually found it yet? Because we actually have not confirmed that Planet 9 is in the solar system. We're still looking. But before I get to Planet 9, let's talk about some of the earlier planetary discoveries in the solar system. So I'm going to start with this schematic of what the solar system was thought to look like in 1650. And I chose 1650 because if I had chosen 1600, I couldn't have included the Galilean moons on this diagram. I could have only included the sun, which we've known about since antiquity, and the 6 planets that are visible with the naked eye, which we don't really have recorded discoverers for because, again, they've been visible since antiquity. And then in the early 1600s, Galileo was able to use telescope-assisted observations, which was only made possible because the telescope was invented in the early 1600s, and then Galileo quickly improved upon it and built a telescope good enough to detect the Galilean satellites, so Jupiter's resonant large moons that had not previously been known about. However, this is a pretty limited picture of the solar system in 1650. Even though we as humanity had invented the telescope and we had started to find some smaller objects in the solar system, there was a lot missing. So I'm going to start by talking about a few planet discoveries that took place in the 1700s, the 1800s, and then one that took place and then was redacted in the 1900s. So I'll start by introducing William Herschel. So Herschel, I think, has a really interesting life story. So he was born in Germany, but he moved to England in order to avoid a war. And he actually did not spend most of his early life doing astronomy. He didn't go to school for physics or astronomy. He actually spent most of his early life working in music. So he actually was a composer even through some of the time where he started to think about astronomical topics. He was also a relatively well-known violinist at the time, although of course today that's not what we know him for. It was not until he reached his late 30s where he actually started to take astronomy and science really seriously. So in the 1770s, he started thinking more about the solar system and telescopes. And pretty quickly, he did a really good job of thinking about telescopes, which is he built his own giant telescope, which at the time, this is when he was 36, he built a 1.8 meter refractor telescope. There's a diagram here. It was amazing, it was ridiculous. It was just a huge technological accomplishment for the time. And this technological accomplishment allowed him to achieve many science goals, which I'll just kind of jump through. He built a catalog of nebula that was used for a very long time. But what I think was his most exciting discovery was the discovery of Uranus. So Uranus was a planet that had been living in the solar system all this time, that people had been observing the 6 naked eye planets, but nobody had seen it. And the reason for this was that it really took telescope-assisted observations for Herschel to be able to see an object dim like Uranus in the solar system. He didn't stop there. After finding the planet, he immediately, a couple years later, discovered some moons of Uranus. And a fun aside, I wanted to point out that Uranus has 28 known moons, but if I had given you this talk 2 years ago, I would have told you that it had 27 known moons, because the most recently discovered moon around Uranus was actually not discovered until last year, 2024. So it's kind of sometimes very surprising to realize how recently we're continuing to discover new objects, even moons in the solar system. So jump forward to 1801. The solar system in 1801 now had Uranus along with some satellites of Uranus. So we're starting to kind of fill in the outer solar system. Also in 1801, the first known asteroids series was found, which we will get back to exactly what that means at the end. But this was kind of the beginning of the characterization of the asteroid belt as well. Now I'm going to jump to my maybe favorite planet discovery, favorite confirmed planet discovery, which was by Urbain Le Verrier in 1846. And Urbain Le Verrier, Uranus at the time that he was doing his work had been observed for a pretty long time, many decades. And Urbain Le Verrier used that data, decades and decades of data, tracking the position of Uranus through the solar system over time. And he noticed something was wrong with Uranus's orbit. What he noticed is he noticed that if you looked at the true position of Uranus, it deviated from what you would expect under the laws of Newtonian mechanics. So at this point, it had been a couple centuries since Isaac Newton had formulated his laws of mechanics that seemed to pretty well describe how objects moved in the solar system, but Uranus was not obeying these laws. So what was Urbain Le Verrier's solution? His solution to this problem was that if there was an additional planet orbiting outside of Uranus's orbit, then the perturbations that this planet exerted on Uranus's orbit, the gravitational tugs that would cause Uranus to be just tugged back and forth over time, could perfectly explain what he was seeing. So it wasn't that Newton was wrong. It wasn't that Newtonian mechanics didn't work. It was just that we didn't know about all the planets in the solar system. There was an extra one. There was something else outside of Uranus. So he, in August of 1846, he wrote a letter to the Berlin Observatory. He actually wrote many letters to many observatories, but Berlin Observatory did get this letter on September 23rd. And when they got the letter, they did something that none of the other observatories he had sent letters to did, which is they actually looked in the sky where he told them to look. And what they found, about within a degree of the exact sky location where he had told them to look, they found an additional planet, Neptune. So this is I just love this story because it's such a good example of someone making a theoretical prediction and then it actually panning out and turning out to be true with observations. So this is the 8th planet discovery in the solar system, Neptune. And it's a little unique because while you usually think about planets as being discovered by telescopes, but in this case, Neptune was discovered by mathematics. So mathematics predicted that it should be in the solar system, and then only later on did astronomers actually go and get the data and confirm it was there. So back to my schematic, moving forward to talk about the solar system in 1870, we have now added Neptune to this population. And it also had a moon that was shortly after its original discovery was also discovered. So again, we're kind of populating this, we're learning more about there's large planets in the outer solar system and they tend to have these moons. Now, I'm going to move on to something else that Urban Le Verrier also mentioned, or also noticed. So in the late 1800s, astronomers were keeping meticulous track of the positions of objects in the solar system. So all the planets and all of the smaller objects that they knew about. And something that was kind of starting to become evident in the late 1800s, in the 1870s, 80s, was the fact that Mercury was not behaving as expected. Now this story is probably starting to sound familiar, because it's very familiar to the Uranus story. So when scientists, including Urban Le Verrier, plotted out Mercury's orbit through time, they realized that it, again, also was not obeying Isaac Newton's laws. So instead, it appeared that its orbit over time was precessing. So basically the direction that the orbit is pointing through space was changing with time. And Newtonian physics did not expect that to happen. So, what's the answer? Urban Le Verrier had an idea, and his idea was kind of the same idea he had for Uranus. It was the presence of an additional planet in the solar system. So this is a screenshot of the front plate of a paper where he predicted this. His chapter, Theory of the Movement of Mercury. So in this publication, and in several other publications that he wrote throughout the rest of the 1800s, he created a very complex and mathematically sound model for how if you had an additional planet in the solar system in between Mercury and the Sun, then that planet could cause Mercury's orbit to look the way it does. So this planet he christened Vulcan, because of how close to the sun it would be. And people started, just like when he had told them, you know, you should go look for this planet outside of Uranus, people started going and looking for Vulcan as well. However, the decades passed, and nobody found Vulcan. And there was a reason for this. The reason for this, you may remember, I said that Mercury's orbit did not make sense under Isaac Newton's formulation of gravity, which was true. And this was what everyone assumed was the true laws of nature. In 1915, we had a new formulation of gravity, the theory of general relativity, by Albert Einstein. And this was a modification on Isaac Newton's previous theory that was one of his many discoveries. Importantly, there were three main predictions of his theory of general relativity. So general relativity, basically the idea, you've probably maybe heard of it before, but the idea is that if you have really heavy objects in space, they will bend space-time. And that means if other objects come close to them, then they will experience not just gravity, but gravity perturbed by the bends in space-time. So Albert Einstein predicted three main things if this theory was true, if general relativity was real. Then there'd be three main things you would see. One of them would be the precession of Mercury's orbit. So instead of on the top here, you can see what you'd expect Mercury's orbit to do in Newtonian gravity, which was not what it was doing, which was why Urban Le Verrier thought that Vulcan needed to be in the solar system. But Albert Einstein found that even if you had no other planets in the solar system, general relativity would adapt that orbit and make it precess with time, which was in fact what we were seeing. There were two additional tests. One was the defection of light by the sun. So basically, if photons from distant stars pass close to the sun, their trajectories will be bent slightly because space-time is bent around the sun. And then the third is the gravitational redshift of light, which I'm sure you guys have had extragalactic astronomers come in and talk to you about redshift before, so you probably have heard all about that. So this first option, the perihelion precession in Mercury's orbit, if general relativity is true, then all of a sudden this explains all the confusion that people had about Mercury's orbit. You don't actually need to invoke an additional planet Vulcan. Instead, it's just this new piece of physics that we did not understand. So it didn't take long before this could actually be tested. So in 1919, Arthur Eddington built this large experiment sending people to 2 different continents to take observations during an eclipse that was happening. And the experiment that he did was when the light from the sun was mostly blocked out, he looked at the location of background stars close to and behind the sun and looked at where their locations appeared to be compared to where the locations were at times when the sun was not right in front of that light. And what he found is that the light from the background stars did appear to be bending in the way that general relativity would suggest that it should. So this was good evidence that the theory of general relativity was true. And this was evidence that Vulcan was not actually a real planet. So Urban Le Verrier, he's 1 for 2. He predicted 2 planets of mathematics. One of them was real. I think that's pretty good. But Vulcan was an example of a planet that was proposed and then didn't end up being a planet because it did not exist. Okay, moving forward in time to other reasons why things might not be planets. So Clyde Tombaugh in the 1930s, he was again taking advantage of brand new technologies, and he used a camera that was connected to a telescope plus photographic plates, and he took pictures of the night sky, and then he kept the photographic plates. What this allowed him to do is allowed him to use something called a blink compactor to flip between 2 different photographic plates that he had taken at different times. This meant that if there was something in the sky that was moving, then he should be able to see it in a different location on each of the images. So here is, there's a spoiler in the title of this, but his most famous discovery using this exact method has these 2 discovery images taken on January 23rd, 1930 and January 29th, 1930. And there's a helpful arrow here pointing to the object that's changing between these 2.
Yeah.
So if you stare really closely, which maybe it's hard to do here, so I'll put them up big, and then I'm going to flip between them. So watch for the arrow and try to see how most everything in the image is staying the same, right? Staying in the same location. And that's because most of these dots are due to background stars, and we are moving very slowly with respect to them, so they're going to appear to be basically the same location over short time spans. But this object that's moving back and forth, which you've already seen the spoiler that it's Pluto, this object is much closer to Earth and the observer than those distant stars are. And so as a result, when you take 2 images on different days, when the Earth's position has changed relative to this distant object, it appears to be in a different location. So this discovery mechanism we're going to be back to later because this is one of the most powerful ways to find things in the solar system. But 1930s, this allowed Clyde Tombaugh to discover Pluto. Now, I don't have to tell you all that Pluto was promoted to be a planet at this time. But I'm not going to put up my diagram of the solar system again because I don't want to be too inaccurate. But we'll just, we'll accept that at the time, people thought Pluto counted as a planet. Now, moving forward in time with our discovery of planets and asteroid planets, in 1951, George Kuiper came up with this theoretical paper that predicted there should be an icy reservoir of objects out past Neptune. And this icy reservoir ended up being named after him, the Kuiper Belt. But he just first predicted that these objects should exist. And they would exist right in kind of the region where Pluto had been found. Now I'm going to skip forward about 40 years in time, because despite the fact that scientists thought we should have this Kuiper Belt full of icy objects in the outer solar system back in the 1950s, it took a really long time before technology had caught up to the theoretical predictions and allowed us to actually find them. So I'm going to put, here's an image of Dave Jewett and Jane Liu, who in 1992 made a discovery of this object right here, which is a little hard to tell that it's actually a Kuiper Belt object, but it was the first transymptonian object discovered ever. Now, jumping forward, there have been many more Kuiper Belt discoveries since then, and I'm going to just put up an animation showing the solar system. So this is in 1991, what was known in the solar system. I've ignored all the asteroid belts because they'll make the diagram much too busy. But this blue circle with a dot on it is Neptune's orbit. So anything further away from the center than that is going to be past Neptune in the Kuiper Belt. Anything closer in will be crossing the orbits of the giant planets. So now this is going to step through time. You can see in 1992, David Jewett and Jane Liu's discovery popped up, and now I'm like super behind because the discoveries are popping up extremely quickly. Since technology had advanced to the point where we actually had the capability of using CCDs plus large diameter telescopes to find these really faint objects the discoveries just cascaded in. And now I'll stop this animation, although it keeps going, because we have a little bit more of the story before we actually get up to 2014. So I'm now jumping forward to the part that everyone probably read about in the news and had nightmares about Pluto's poor end at night. So in 2005, Mike Brown was one of the astronomers who had been contributing to this just deluge of discoveries of objects in the outer solar system. So he was a part of many of the early large discoveries of really exciting new objects, including objects that were part of families of objects that we think came from a collision, as well as really large objects. So this is the controversial one. So in 2005, he discovered Eris, and we have here discovery images showing its position changing with time, which you can probably tell it's moving a little if you squint. But there was something very unique about this object, because this was not the first object found in the Kuiper belt, right? Like, these objects had been found previously. We had a decent number of them by 2005. But there was something really unique and special about this object, and that was that it was physically heavier than Pluto. So not only, it's radius-wise slightly smaller than Pluto, but it's physically heavier. It has a greater mass than Pluto. And I'm putting on this diagram a comparison of those two objects, Eris and Pluto, to Haumea and Makemake, who are two other objects in the Kuiper belts that are kind of pretty large in size. And then, of course, Ceres is from the asteroid belt. Now, again, these discoveries were kind of just flowing in. They were being discovered constantly. Like, these three bottom objects were discovered within a couple years of each other. And something that people started realizing was they started realizing that Pluto wasn't really that special. Like right, it's kind of sad, but for 70 years we had thought Pluto was a planet, it was really unique and special in the outer solar system. But it was really starting to look like Pluto was just kind of one of many similar objects that we had in that part of the solar system. And Clyde Tombaugh discovered his object 70 years before these objects, which is really impressive, but there was a huge number of them. So this resulted in the International Astronomical Union making a formal definition for what counted as a planet. The concern at the time was that since we were finding so many objects that were similar to Pluto, that the solar system was going to quickly balloon into 10, 15, 20, 50 planets if we called everything that was like Pluto a planet. And that did not seem reasonable. So the International Astronomical Union got together and they came up with a formal definition for what actually counts as a planet, which they hadn't done before. So there were three criterion that something had to fulfill in order to be a planet. So the first, it has to orbit a star. So as a result, even though we have in the solar system some moons, like Ganymede, that are physically larger than some planets. Ganymede is physically larger than Mercury. Ganymede does not actually get to be a planet because it's orbiting a planet instead of orbiting a star. So if you want to be a planet, you have to be orbiting a star. Second, it needs to be big enough such that it has enough gravity to force itself into a spherical shape. You've probably seen images of small objects from the asteroid belt or the Kuiper belt that are irregular shaped. They look kind of just jagged and they don't look like circular or spheres at all. Once an object gets large enough, it attains the state we call hydrostatic equilibrium, which results in a spherical shape for large enough masses. So if something is going to be called a planet, it needs to be large enough that this condition is met. Now, so far, so good. Pluto and Eris and many of these other objects do satisfy these two criterion. But the one that did Pluto in was the third, which was that for something to be a planet, it has to have cleared its orbit, which means that there needs to not be a bunch of similar objects on the same orbit. And for Pluto, there's actually now a class of objects in the outer solar system that we call Plutinos because of how similar they are to Pluto. So Pluto was not even close to have cleared its orbit. There were too many similar orbits for it to be a planet. So as a result, Pluto was demoted from being a planet into a dwarf planet. And Mike Brown got a lot of hate mail for this. And he embraced this, you know, he wrote a book about how he killed Pluto and it had it coming. But it's been very controversial. So all of these objects that we could have maybe called planets in fact, none of them are planets. We instead call these objects that are large enough and orbit the sun, so they meet the first two of these criterions, we call these dwarf planets. And we actually, the number of dwarf planets we have in the solar system is rapidly increasing. Okay, so I have gotten closer to modern day, and we now have added to our diagram the Kuiper belt. So that includes many dwarf planets, Pluto is one of them. This is where we're going to spend the rest of today talking about, is in the Kuiper belt. And the reason for this is that, again, we, throughout history, have basically been using technology to push the frontiers of what we can discover in the solar system out further and further with time. As we build larger telescopes, we build better detectors. In the modern day, we build better computer algorithms to process the data that we get. So the real frontier for discovery in the solar system, at least in my opinion, at this point is the Kuiper belt, where there are a huge number of objects that we still have not discovered. Now I've gotten to, I think, maybe the exciting thing that everyone was looking forward to hearing about, which was the proposal of Planet 9's existence. Now, when I say Planet 9, I'm not talking about Pluto. Pluto was demoted a decade before this, no longer a planet. The position of the 9th planet in the solar system was therefore open for a new planet if we found one. So Mike Brown and Konstantin Batygin in 2016 predicted the existence of an additional planet in the solar system, something much, much more distant from the sun than Pluto, something much, much larger than Pluto as well. Now, why did they actually think that this was here? They had evidence, and the evidence came in the orbits of the objects in the Kuiper belt. So I'm going to show this animation here. So that's the inner solar system. The outer one was Neptune's orbit that just shrunk down. So I'm going to jump back so you can watch for that. So the outer circle there is Neptune's orbit. Now we're jumping down, and what we're plotting here is the orbits of trans-Neptunian objects. So these are the most distant objects we know about in the solar system. Well, as of 2016 is these ones. And if you're looking at these orbits, I'm going to pause it so we don't get any spoilers. If you're looking at these orbits of objects, what do you notice about them?
Very eccentric.
Very eccentric, yep.
And they're all eccentric in the same direction.
Okay, there you go. You have discovered Planet 9. So this was this was exactly what Mike and Konstantin noticed, was that these objects, their orbits all appeared to point in the same direction. And that is not something that you would expect if you had a symmetric potential. So if you had only the solar system that we showed in the animation existing in the solar system, then there would be no reason for these to all be pointing in the same direction. So Mike and Konstantin noticed that, and the hypothesis that they came to was that there should be a 9th planet in the solar system, basically pointing the opposite direction as all of these trans-Neptunian objects, and the existence of that planet and the gravity it provides would shepherd these smaller objects into the orbits that we see.
Huh.
So I'm going to show you this is actually a piece of art that a magazine that wrote an article on one of my papers made that I think is a really good kind of demonstration of emotionally what this means. So here is the actual solar system. Trans-Neptunian objects would exist somewhere out here with their orbits all pointed in a direction. And then Planet 9 is basically the counterweight that's both providing the shepherding of their orbits and also allowing them to stay stably in those orbits. So this fundamentally was the reason that Planet 9 was first predicted to occur. It was this clustering of the orbits of all of the trans-Neptunian objects, and you need something to explain that. So they considered several different hypotheses in their original paper, but most of them could be disproven except for this existence of a 9th planet. Now, at the same time as that was happening, I'm going to get back to this animation of the Kuiper belt object discoveries. And this entire discovery of Planet 9, the hypothesis of Planet 9, since it hasn't actually been discovered yet, was taking place in around 2015 to 2016 when the paper was published. As this was happening, many more objects in the outer solar system were being discovered. So when Mike and Konstantin first came up with their hypothesis, they only had a limited number of these objects. But as you're about to see when the animation continues past 2016, more and more objects continued to be discovered after that. So now, this is also my personal entry into this story. So my role in this kind of quest to find Planet 9, which has not yet been finished, came when I started working with the Dark Energy Survey in around 2015, when I was a graduate student at the University of Michigan. And the Dark Energy Survey was a survey that, from its name, you can probably figure out, it intended to study dark energy. And its basic strategy was to just take pictures of the sky repeatedly. And part of what they were trying to do is look for supernovae that go off, because if you see something, you see blank sky, and then you see something bright, that could be a supernova if it just appears out of nowhere. So their survey strategy is basically just take pictures of the sky, of about 1/8 of the sky, continuously, using DECCAM, which is a really good camera on the Blanco 4-meter telescope in Chile. And this was intended mainly, again, for dark energy and for supernova science. So here's an actual image showing a supernova going off, where in the first image here, the template, you see there's no dot above this kind of galaxy-looking thing. And then in the second image, there is. So that would indicate that, well, you have to prove it actually is a supernova, but something like this could be a supernova going off. Now, there was really one annoying thing that Dark Energy Survey had to deal with, which was they're looking for transients that are supernova. But sometimes these annoying foreground objects in the solar system would just pass in front of their cameras. They just fly by. And they, this is very annoying to them because those were not supernovas, the asteroids and the Kuiper belt objects that were just passing in front of their cameras. But sometimes they could mimic the appearance of one because they wouldn't be in one frame and then they would be in the next frame. This became our raw data. So basically the things that were really annoying to the people doing dark energy actually allowed us to learn a lot more about the outer solar system. So you'll notice that this image looks a lot like the ones that I showed you of Clyde Tombaugh's 1930s photographic plates that he looked between with a blink compactor. And it also looks a lot like the images that I showed you of Eris's discovery by Mike Brown. This is 2 different images from DECCAM data taken by Dark Energy Survey that shows a solar system object moving from one frame to the next. You can see again, just like with Pluto and Clyde Tombaugh's discovery, everything else, the background stars, are staying in about the same locations, but then this one object highlighted by the green dot is moving from one frame to another. Okay, before I get into what we did with this data, I first want to introduce you a little to the categories of objects that we might expect to find in the outer solar system. So ever since Gerard Kuiper first predicted the existence of the Kuiper belt in the 1950s, which he didn't call it that, but it's come to be named after him, we have been classifying more objects and trying to sort them into categories and understand how they're different from each other. So this is an image from a review article that Konstantin, Fred Adams, Mike, and I wrote in 2019. And it shows the different populations of objects that exist in the solar system. So the first one up here is called a centaur. And centaurs are objects, oh, I should explain the axes also. So on the x-axis here, we have the semi-major axis. So that's on average, how far away is the object from the sun. So the things out here are very far away. The things here are close. We have a line here at 30 that denotes Neptune's orbit. Then on the y-axis, we have the eccentricity. So if you're down near 0, then your orbit is pretty circular, kind of like Earth's orbit. And then as you get up to larger values, your orbits are going to look more like those on the diagram I showed you of the trans-Neptunian objects, all pointing the same way. They're going to look like really stretched out ellipses. So the first population is centaurs, and centaurs are objects whose orbits cross the giant planets. So they spend some of their time, for example, inside of Neptune's orbit and some of their time outside of Neptune's orbit. These objects are subjected to extreme dynamical violence because when they pass close to Neptune or the other gas giants, they can just be scattered in any which way. So the centaurs are really hard to use to understand the long-term history of the solar system, because when we see a centaur in an orbit today, we don't necessarily know that it was in that orbit 100,000 years ago or 1,000,000 years ago. It might have been very strongly perturbed by one of the giant planets. One step down in dynamical violence is the scattered disk. So the scattered disk is objects that come close to Neptune's orbit, but they don't quite cross it. So they spend their entire lifetime outside of Neptune's orbit, but do come kind of close. And the name scattered disk comes from this idea that the objects could potentially be scattered off of Neptune. So they're not going to be perturbed in the same extreme way the centaurs are, but they might have their orbits somewhat changed. Down here we have the classical belt. So the classical belt is when you think of when an astronomer thinks of a Kuiper belt object, it's what you think of. It's kind of on a circular orbit, it's probably made of ice, So I might say they're kind of boring, but there's things you can learn about them. Finally, we also have detached Kuiper belt objects. So these are ones where they don't actually come close to Neptune. They stay pretty far away from Neptune at all times. These are really hard to discover because they don't come close to Neptune, and so since they're so far away, they're very faint because we detect these objects via scattered light. So the sun emits light, hits the object, it's scattered back to us. The further away the object is, the worse that process becomes, the less light we get back. So the detached Kuiper belt objects are hard to discover. They're also hard to explain because to explain the origin of a detached object, you have to explain how it became so detached from the gas giants and the rest of the Kuiper belt. Okay, so back to our data. Now I've introduced kind of the different places that we are looking for objects in the Kuiper belt. So this is what individual data frames look like, the pictures of the sky that we use. But to turn this into a form that can actually tell us about a single object, we have to take these images and we have to link them together. Because when we get these images, we don't know which ones correspond to the same object. So we have to go through the hundreds of thousands of images that we have and figure out which of the frames have actually the same object in it and then link those together. When we do that successfully, this is what it looks like. So this plot here is showing the motion that one of our discoveries took across the sky from 2014 to 2017. And we have the right ascension, x-axis, declination, y-axis. You guys all know what that means. So the red points correspond to the locations where we observed this object to be over time. And the exact shape of this kind of curlicue path that it takes over the sky, this is due very, very small amount due to the motion of the object, but it's mostly due to Earth's motion. So this is due to the parallax of Earth. If you are able to, and I will skip over some of the technical details, but if you're able to successfully combine all of these little observations, each of these pictures is one red point, into a diagram like this, then from this you can get the orbit of the object that you found. So we did this for hundreds of objects in Dark Energy Survey, and here is a classification of the objects we found and where they fall into these categories. The centaur objects, which are the ones that are perturbed very strongly by the giant planets, the detached objects, which are kind of hard to understand, and then the scattering objects, yellow, which are ones that have interactions sometimes with Neptune, but are expected to keep their orbits outside of Neptune for their entire lifetime. Now, I'm not going to go through all these objects because there was really one, which is the one that I showed you the diagram for, that turned out to be the most interesting. And the name of this object is 2015 BP 519. So all objects are named by the year that you first found the detection, plus a 2-letter, 3-number identifier, up to 3-number identifier that tells you what order the observation was reported to the Minor Planet Center, which is kind of the database of all of these objects that is maintained by astronomers. So this particular object, you'll notice that even though it says 2015, we actually had some observations in 2014. And the reason that it's not a 2014 object is we didn't find those until later. So originally we only knew about these ones, then we went back and found these after the fact. Here is, if you turn those sky images into an orbit, The blue line is what this orbit looks like. This plot is similar to the movie I showed you. The black line, the black circle there is Neptune's orbit, and then all of the other ovals are trans-Neptunian objects. And these are the same class of objects that Mike and Konstantin used to predict the existence of Planet 9. So this is basically their plot, except updated because it has a few new objects that hadn't been known at the time that they did their initial analysis. They published their paper in 2016, and although we knew about the object in 2015, we didn't actually publish it until 2018. So we had some other objects that were discovered in the meantime. Now, the thing that was really unique and why this is my favorite object that we discovered out of Dark Energy Survey is that if you look at, so the gray plane is the plane of the ecliptic, and then white or lighter colors denotes that you're above the plane, darker colors denotes you're below the plane, so it's kind of a 3D image in 2D. And if you're good at interpreting these images, then you might be able to tell that BP 519 is much more tilted angularly than the other objects. So this object has a very high orbital inclination. So inclination is what we call the angle of the tilt between the plane of the solar system and the plane of the Kuiper belt object. It has a very high inclination for this type of object. So it has actually the highest inclination of any trans-Neptunian object that we've discovered. Now, this was very weird. So I spent a lot of time and many months running simulations on this object because the standard planet formation theories only predict that objects like this should have inclinations of up to about 40 degrees in the solar system. But this object had an orbit of 55 degrees. So I ran a lot of simulations of solar system evolution, trying to figure out, could you have a really lucky interaction with Neptune where you just happened to throw this into a high orbit? And none of my simulations were able to successfully reproduce the orbit of this object until I added Planet 9 into the simulations. So the second that I started my simulations with not just the solar system planets, but the solar system planets plus this new hypothesized Planet 9 that Mike and Konstantin had predicted, all of a sudden, not only was this object's orbit explainable, but it was actually very natural. Planet 9 created objects that looks just like this. So this is an article written in Quantum magazine about this object, which is it's a dwarf planet itself. It does not yet have a formal name. We're working on it. So right now it's just 2015 BP 519. But the idea here, this is another image that Quantum magazine made that was pretty good. The idea here is that our object has a really large tilt compared to the plane of the solar system. And Planet 9 is the only mechanism that we were able to recreate this really large tilt with. So, does this prove that Planet 9 exists? It does not prove it. But we don't have a better hypothesis for how this object attained its current orbit. So we published this object in 2018, and that same year, Konstantin wrote a paper explaining all the details mathematically of how Planet 9 would cause these objects to be generated. So this is an updated plot now of all of the objects that we know about that are in this class of trans-Neptunian object. And you'll notice that there's a few that don't point in the same direction of the original cluster. So the original cluster is in this direction, and there's a few others that don't point in that direction. But even as more objects have been discovered over the past several years, the clustering appears to hold up as being very strong. Now, I have to stop here, and I have to tell you that not all scientists agree. Planet 9 is a very contentious topic, and I've been to conferences where there have been some, the astronomers' version of a fight over the evidence for Planet 9. So what I'm going to show you here is I'm going to show you why people think that this might not be necessary, why the Planet 9 hypothesis might not be needed. So this diagram shows an image of the sky with the different colors correspond to different surveys that have discovered trans-Neptunian objects. So on the top we have these two guys, Scott Shepard and Chad Trujillo, who discovered a huge number of objects just on their own. Second one is OSIS, which is a large survey that's searching only for solar system objects. The dark blue is Dark Energy Survey Wide Survey. So Dark Energy Survey is the group that I worked on, the wide survey is the eighth of the sky, and then the yellow regions are the supernova fields, which is basically just much higher quality data than the background. Now, the thing that people pointed out fairly quickly was that we aren't actually looking everywhere in the solar system for these objects. And additionally, we can't find every object that's in the Kuiper belt. I mentioned earlier how there's these detached objects that are really hard to find because they're very far away. This is true generally. It's a lot easier to find an object that's closer to us than an object that's further away. So as a result of these factors, among other similar factors, this fact that we're not looking everywhere in the sky, we can't see every object because some are too small or too far away. There's also choices that are made by observers. So for example, Scott Shepard and Shad Trujillo, who do such a great job at discovering objects, they have to choose where they look. They can't look everywhere. So all of these factors together contribute to something we call observational bias. It's the idea that our observations are limited by all of the biases that we have put into it. And so we're not necessarily finding objects that correspond to the true population of objects. We might be finding a non-representative population. It's like, if I go out into town and I'm looking for a football fan, I'm going to find a Packers fan, right? If I go out in Texas, I'm going to find something different. So what many astronomers thought is they thought, okay, well, all these factors of observational bias could mean that we're actually only finding the objects that we can find. And so the reason they're all pointing in the same direction is that that's just what we can find. Before I move on to where we've looked, I'll say this is not a resolved topic. So many groups have done analyses using the available data, trying to figure out if this is observational bias or if this is not observational bias. And many different groups have gotten many different results. So we have no solution. Yes?
What's the red median there?
That's the ecliptic.
Oh, okay. I'm not used to it being
Yes,
sideways.
right. We have some strange projections.
Okay.
The red line, yeah, Rick's asking about the red line in that diagram, and that's the ecliptic for home.
All right, so I'm going to move on from the bias issue because I can't talk about it too long because we don't have an answer. So the important thing to take away from this is just the idea that there might be observational bias. Well, there is observational bias that's causing an effect. The question is the effect large enough that it's completely controlling the objects that we discover? And we mathematically do not know the answer to that yet. So the next topic is we have a prediction for where Planet 9 should be that Konstantin and Mike came up with. Where have we looked? Like, we haven't found it yet, but where have we actually looked for it? So the first place that many different groups have looked is in existing data sets, like Dark Energy Survey, that have been taking data over a long extended baseline of time. So Pan-STARRS is one example of a survey, Dark Energy Survey, Wiki Transient Factory. These are all different groups that have taken data using telescopes, images of the sky in either the optical or the infrared. And if you look through all of that data, like we did with the Dark Energy Survey data, you can discover not only transit-Newtonian objects and Kuiper belt objects, but if Planet 9 was visible, you could theoretically discover it as well. None of these groups have been successful, and there have been dozens of academic papers on this topic. No one has found it. Next really cool idea was a group used Cassini ranging data to try and detect the gravitational influence of Planet 9. So the idea being that the Cassini ranging data gives us a very precise, relatively precise measurement of the distance between Saturn, Cassini, and Earth. And that distance, if Planet 9 is in the solar system, will show some fluctuations due to Planet 9's signature. Now, this data did not find any evidence of Planet 9. It's unclear if this is due to the precision of the data or if it's because Planet 9 is too small to cause these fluctuations. Another way, exactly, right, too far away. If it's too far away, then it's just not going to have a large enough signal. Another thing people have done is actually go out to the telescopes themselves and look in the part of the sky where they think that Planet 9 could be. And this is kind of the Berlin Observatory discovering Neptune strategy, to actually just go out and hunt for it. And this is something that Mike has done quite a lot at Keck, but he's not the only one. There's a lot of groups who are actually actively going to the telescope and looking for Planet 9. So far, obviously, it has not been found, at least not that I know of. So since we have not actually found it yet, we do get some information from all of these places that we've looked. But what we don't know is it happens to be in the place where we haven't seen it, or is it just we're looking for something that's not there, and so we are never going to find it. If you do combine all of these places that people have looked, what you get is you get a map. So this is from a paper that Mike published last year in 2024. This is a map of, based on all of the non-detections of where Planet 9 was not found, where could it actually be? And the darker blue regions correspond to lower probabilities, the brighter regions correspond to higher probabilities, and we at this point know that Planet 9 needs to be pretty far away at the furthest part of its orbit, and we also have kind of placed an upper limit on its mass, so that we think it's actually slightly, if it exists, it's slightly smaller than it was originally thought that it might be. So, what next, right? We have, Planet 9 was proposed almost a decade ago now. We have been spending that decade looking for it, and we have not found it. So, what is the next thing that we can do? There is actually a lot of hope, and this hope comes from Vera Rubin Observatory. So Vera Rubin Observatory is a telescope that's been being built for a very long time, which is going to have first light and start taking science data this year, 2025. And Vera Rubin Observatory is kind of like a dark energy survey on steroids. So instead of only surveying about an eighth of the sky with a 4-meter telescope, it's going to survey the entire sky with an 8.5-meter primary mirror telescope. And its camera weighs about 3 tons and is much better than any camera on previous telescopes. So Vera Rubin Observatory is going to run the legacy survey of space and time, which is going to take images of everywhere across the night sky repeatedly. And what we're going to get out of this is we're going to get huge amounts of data, so roughly 20 terabytes of data a night in just images of the sky. And these images are what we've been using to discover Kuiper belt objects with for so long, but they also will hopefully allow us to not only discover more Kuiper belt objects, which will allow us to pin down a little better where Planet 9 should be, but it also might allow us to discover Planet 9 itself. So I want to show you just the image of the camera, this 3-ton camera. It's very cool. And with that, I only have a few minutes left, so I'm going to edit my title slide and say that, really the search for Planet 9 is not over yet. It continues. We'll see if Vera Rubin is able to make some more progress that previous surveys with much smaller telescopes and worse cameras weren't able to do. So keep your eyes peeled in the news. Hopefully we'll all learn some good news soon. All right, if you have questions, I'd love to take them this time. Thank you so much.
That was a fantastically interesting. Yeah, I loved it. One question I have, there's one very obvious observational bias of all of these objects that we're looking in the Kuiper belt, and that is we're seeing they're all going to be fairly close to apogee. Is that correct?
Yes.
And how far out can we actually see? What's the farthest that we see in AU?
Yeah, so good question. Yes, we are very strongly biased at finding things near closest approach, so near perihelion. Now, we actually have found objects out to about I want to say 65 astronomical units present distance. So some of these detached objects, they actually come no closer than 50 to 60 astronomical units. So we can find objects further out. The trick is that those objects need to be bigger for us to be able to find them. So there is a huge pile of observational bias inherent in that. However, the fact that the objects are clustered in one direction is not really inconsistent with the fact that they're discovered at closest approach. Because if you had uniformly distributed objects around the outer solar system, they would all have a closest approach, and theoretically we could find the other objects at their closest approach, because the closest approach always occurs near Neptune's orbit for trans-Neptunian objects.
Yes, equally fascinated by this presentation, but wanted to ask, what if Planet 9 was not a planet, but something that's gravitationally equivalent, but much smaller, like a black hole?
Yeah.
And you would be looking at a very different type of, for a different type of object from your observations than looking for a planet.
Yes, so I hear some laughs, but this is actually a valid scientific hypothesis. There was a paper written by astronomers proposing that Planet 9 could be a low-mass black hole. I mean, the black hole mass spectrum, how small primordial black holes can be, that's something we haven't fully determined yet. So we cannot rule out Planet 9 being actually a black hole. Konstantin likes to say we also can't rule out it being a hamburger. Occam's razor tells us it's most likely to be a planet. That's kind of the thing that's most consistent with our understanding of the universe, but I would not rule out it being something like a black hole. We can't rule that out.
Yes, sure.
Just curious, the three criteria for being a planet, when something's that far out, as Planet 9 would be, with an orbit of what, 25, 50,000 years, how can you actually prove it's actually clearing its orbit?
Yeah, that's a good point. I think that, so something as large as Planet 9, which we think is probably something like 6 Earth masses.
Thank you.
Yes,
That
yeah.
was my question.
Okay, well, great question. Yeah, so we originally thought it was between 5 and 10, and all of this data that we found has kind of made us think it's smaller and smaller. So now we think it's like 6 Earth masses. So something like that probably did not form where it is. We can't rule it out, but we think it probably did not. Our current understanding of planet formation is that you're not going to form objects that large, that far out, because the protoplanetary disk wouldn't have enough mass to form something small enough to be a planet and not like a star, but also 6 Earth masses. However, to your question of could we actually rule out that it had could we prove that it had cleared its orbit and there were no similar objects out there? I think it's very hard to disprove the existence of objects that are just too small for us to see. So I think it would be more of a Pluto situation where we'd say, okay, we think it's a planet, and then if in 100 or 200 years people come back and find 5 others, which I think is unlikely, but if they did, then we'd probably have to demote this Planet 9 as well.
So with a couple of assumptions in place, assuming that you can approximate its mass, and you can approximate based on where it is, its composition, and therefore things like its albedo and orbital speed and semi-major axis, are the instruments that we have available able to actually detect such a planet, assuming that it's at aphelion, for example?
Yes, so that is a great question. And the answer is in this diagram. All of the dark blue, if it were in those places, then the answer to your question is yes, we would have been able to detect it. All of the parts that are kind of green, yellow, red, then the answer to your question is no, we would not have been able to detect it. So sometimes yes, sometimes no, really depends on where it is in the sky.
Thanks. I also wanted to say I think it was kind of elegant how 300 years after Charles Messier, you guys have kind of the same way of discovering these objects. These are things that other people don't want, and they're in the way of their observations, but you're compiling, quite the list. So.
That's true, that's a good one. I'm gonna have to steal that.
20 terabytes a day, do we have the processing power to keep up with that and find this stuff in almost real time? Does it exist already?
Yeah.
And the programs there and all that?
So that is a wonderful question. And in fact, the engineers on Vera Rubin have been working on this for more than a decade because it's not easy, right? My laptop cannot do it. My computer on campus cannot do it. Even the super computers on campus, it would be hard to handle it. So the way that it's going to work for Rubin, which is going to be a little different from previous missions, is that Rubin has a centralized data processing facility. And if you want to access their data, you will do it through their interface instead of like what you do right now for some other missions is I just download the data to my laptop and then I work on it. So it's gonna look a little bit different to work with Rubin data than it has to work with other types of data. But you're completely right that this is like a huge technological challenge.
You hinted in one of the previous answers that you do have some formation hypotheses for this.
Yes.
It sounds like it would probably, from my eye, I'm not a professional at this, but it's either something that got ejected from closer in or captured over the solar system's 4 billion year history.
Yes, well, so glad you asked that. So,
Suck it, Rick.
this is an image that I made for the review that I wrote with Konstantin and Mike in 2019, and I'm very proud of how it looks, so I'm so happy to have the chance to show it. So these are the 3 hypotheses that we have. So the first one is in situ formation, that it just forms in its current location. We kind of think this is unlikely, because it's maybe possible that you could tune a disk to have the right parameters to get this exact mass of planet, but it's unlikely. But we can't rule it out. It's really hard to rule things out. The second hypothesis is kind of what you were alluding to. This idea that you first form a solar system, and the solar system had not the 4 gas giants, but had 5 or more planets. And this is actually a prediction of many solar system formation models, is that the outer solar system should have formed 5 planets, potentially. So this part is not ridiculous. Now, the second part is that you have to then scatter Planet 9 onto a high eccentricity orbit, so its orbit looks more like a comet than a planet. And this could happen due to interactions with the other planets. Like, Planet 9 is a lot smaller than Jupiter, so an appropriate interaction with Jupiter or Saturn could potentially toss it out. But toss it out with not enough velocity that it's lost entirely from the solar system, basically just enough velocity that it doesn't reach escape velocity and it stays bound. Then the third stage would be that you'd then have to circularize the orbit because it no longer looks like this, we don't see it. So this could happen via interactions with passing stars. So passing stars slowly exchange energy and angular momentum with Planet 9 and its orbit circularizes with time. Then the third hypothesis that we came up with was that Planet 9 could actually be an alien from outside the solar system, and it actually formed around a different star than the sun. And then at some point in the past, the sun came close by that star that birthed Planet 9, and then Planet 9 could have been captured by the sun. And this may sound kind of outlandish, but a scientist at Georgia Tech, Gonji Lee, did a huge number of simulations a few years ago, not particularly for Planet 9, but just for planets in general. How often can this happen? And she found that it happens like a couple, like 2-3% of the time. Systems will steal planets from other systems. So it's, maybe not a super likely event, but it's possible. Thank you for that question.
You can't rule it out.
Exactly, we can't.
Well, there's also a theory that's why Saturn and Jupiter are out as far as they are, where most other solar systems we find hot Jupiters that are in closer to their star.
Yes, so we do have something very special in the solar system, which is that the Kuiper belt, the reservoir of small objects, allowed Jupiter and Saturn to scatter a lot of energy that might have otherwise changed their orbits and made them, actually we would have expected them to scatter out. Hot Jupiters probably form via different mechanisms entirely. But you're right that there's something special, we think, about Jupiter and Saturn and the Kuiper belt in our own solar system.
Hi, so I'm not trying to be a smart aleck, but I noticed you said that centaurs are Kuiper belt objects that cross the orbits of Neptune or Uranus. So does that mean Pluto is a centaur? Because it does cross the orbit of Neptune. So.
Yeah, so I guess technically it would count as a gas giant crossing centaur. We call it usually a Plutino because it's in a resonance with Neptune. And so it's the prototypical member of the class of resonant objects where you don't get the same scattering interactions you have as centaurs because their interactions with the planet is on a resonant frequency. So you basically have a stable pattern of conjunctions that does not cause like massive destabilization. So I would say under the definition I gave, you'd be right, but also Pluto's kind of special because of that resonance.
Is its projected mass too small to show perturbations in comet orbits?
So Planet 9 is far enough out that if you're talking about comets that pass into the inner solar system, its effect would be very, very small comparatively to Jupiter's effect, yeah. So it would be kind of, like with the Cassini ranging data, it would be a small enough effect that we wouldn't expect to be able to see it with our measurement precision.
For the discovery of Neptune and the solar system discoveries that occurred before then, would those observatories have been able to make those discoveries with our current levels of light pollution?
Oh, light pollution. That's actually an interesting question. So I'm going to answer yes, but that is partially based on the fact that observatories, like historical observatories, can still observe Uranus and Neptune today. Like that is something they often do for like outreach events. So I'm going to assume yes, but that's actually an interesting idea. If you moved Berlin Observatory into the middle of New York, then I don't know.
Does anybody else have any other questions? I know Jürgen's got a question. Anybody else? All right, I guess this will be our last question then.
2 bites at the apple. First of all, I think the data analysis part of it, the Large Hadron Collider has actually been doing a lot of that same stuff with enormous petabytes of data. So I think this is a problem that they kind of started the swimming, and I think other projects are now jumping onto it, and it's an amazing technology of tiered computing. But the other question I have is whether or not there's any mixing between the Oort cloud and the Kuiper belt, and if that's a potential source of the Planet 9.
Yes, so that's an excellent question. So the Oort cloud, we think there are exchanges between the Oort cloud and the Kuiper belt. So objects that maybe originated in the solar system and then moved outwards into the Oort cloud, and then also vice versa. A lot of this would be driven in the absence of Planet 9. Basically, the only force that would be driving it would be the galactic tide. In the presence of Planet 9 can shake up the populations a lot more and cause transition of objects from one population to another population. So I think the answer is different if Planet 9 is real or if Planet 9 is not real. It's a lot easier to move objects between populations with Planet 9 in the solar system. And there are a couple objects that we've found. I didn't highlight them, but they were on my dark energy survey diagram. There's a couple objects that have been discovered that we think are candidates for maybe having Oort cloud origins. But again, it's hard to prove definitively.
All right, Juliette, well, thank you very much. This has been kind of a presentation that's a bit different than what we normally get here. So your information and this topic is greatly appreciated. I enjoyed it very much. And just show you our appreciation for you being here tonight, I would like to present to you this official Madison Astronomical Society mug. For doing as a coffee mug, but there's all sorts of other different beverages that might go into a mug. So I hope you enjoy the beverage of your choice, and thank you so much, and I hope we hear from you again sometime in the future.
Well, thank you, and thank you all so much for having me. I had a lot of fun talking to you guys about this today.
Good, thank you.
So that concludes this month's meeting of the Madison Astronomical Society, and we'll see you all here on Friday, July 11th.